Well, welcome everybody to another one of our podcasts. This is Hugh Waters over in Gloucestershire here, and Phil, I think you're over in London town still?
Yes, in the Route 6 workshop.
Excellent. And today, this is just a quickie today, where Phil had a day out. He was allowed out from work, and he went to find out a bit more about what was HD Masters. But things have moved on. It's no longer called HD Masters, Phil.
That's right. This is this little one day. Well, it used to be a 2 day. It's a 1 day conference now in London. It was held at BAFTA. Really nice venue. Nice setting. In the past, it's just been called HD Masters, but of course now we're very, very used to HD and all that kind of stuff. I think last year it might have been called 3D Masters, but it was just all the manufacturers of greater than HD resolution equipment, and it's a funny mix of manufacturers and broadcasters and kind of other resellers and people like that. And so you get some funny things. And one of the things that really interested me was a lot of what drives these people is sales of television sets. And apparently, panels peaked in 2010. They sold 51 million panels in Europe in 2010. Good grief. But it's just been a linear drop-off since then. So they sold 30 million panels in Europe last year. And the worry is that a nice HD capable panel should last you 10 years, and if it's going to last everybody 10 years, the market's saturated. Why is anybody going to buy another panel? And kind of 3D has been a disappointment. Lots of people bought 3D tellies. In fact, you're hard pushed not to buy a non-3D telly nowadays. And people were obviously early adopters were disappointed that they bought 720p tellies. So I think people are very wary now of investing in new equipment.
Stung too many times.
Exactly, yeah. And why on earth should I waste my money on a 3D telly? When there's really no content for it, it's not very compelling anyway. I've got up a picture of Samsung's booth at NAB this year, and they were showing some 4K 100-inch tellies. I mean, these things are monstrous. Not very many people could fit one of these in their house. And that's the other driver, isn't it? Why on earth do you want tellies? I mean, when I was a kid, a 21-inch telly was considered a big telly. And now 32 really is the starting point, and 55-inch seems to be the kind of thing that if you've got any amount of money to spend, you spend on a telly.
I suppose what's going to happen is that the television is actually going to change eventually from the thing that we watch in the room to being a part of the actual room itself, one whole wall, I suppose. But
well, possibly, but the thing I heard everybody say was, my kids don't watch telly, and I can testify to that. That's my true. Children they don't sit down and watch the television anymore. They watch iPlayer, they watch lots of YouTube, they get their media from lots of different places, but they're either watching it on a laptop or on a tablet or on their telephone. And it's very rare for my kids to actually watch the television. What a surprise kind of thing. But we're broadcast engineers. We've got to be concerned about all this stuff, and so I thought we'd sort of kick off by going over some of the standards that are now governing, this new 4K stroke 8K television, sometimes referred to as ultra high definition television.
That always makes me laugh, because I remember HD was once 405 line.
Yes, that's right. Yeah. There's a great plaque which I use a photograph of in some of my presentations for work, where at Ali Pali, where the 405 line service started by the BBC in 1937, and high definition television started here. So everybody's talking about 4K or Quad HD. You hear that sometimes mentioned sometimes, and it's or UHD, ultra high definition television 1, whereas UHD TV 2 will be 8K television. The thing to bear in mind is that these resolutions are, well, they're either 340 by 2160, so 4 times the resolution of our 1920 by 1080 HD, or they're 7680 pixels across the width of the screen by 4320 pixels deep lines of video. But they're different resolutions to what people are traditionally using for film production, which is 4096 pixels wide or 8192 pixels wide. So if you're shooting something on a 4K camera, you're not shooting at these UHD TV type resolutions. You're shooting at the slightly higher res film standard. But, as equipment, generally speaking, adapts to the standard nowadays, doesn't it? It's not like the old days when it was either PAL or NTSC. Everything works with everything. The thing I thought was very interesting. So EBU Rec 2020 is the standard that covers this. We seem to have jumped from 709 to 2020 very quickly.
Yes, what happens to all the others?
All the standards in between. But one of the interesting things is, and I've got a picture of the 709 colour space up at the moment, which shows the colour space that we use for television nowadays, with D65 as our white point right in the middle there, and the triangle which shows the gamut, the colour gamut of television. But if we look at the Rec 2020 colour space, which I've just overlaid on top of that, the triangle is monstrous. It almost reaches to the limits of human colour perception as defined by the CIE 1931 charts. There's only a few greens that don't come into this new colour triangle, and it's even bigger than the P3 Digital Cinema Initiative, the DCI colour space. So this is something for the future. This is something that we won't see on domestic televisions, I think, for probably 10 years. The ability to, cover this whole range of colours that are now proposed.
So the proposal actually covers beyond what we can actually manufacture at the moment.
Yeah, for sure, yeah. And in fact, we also find ourselves with a new set of colour primaries, which I've just got the values up on screen for. They obviously relate back to the CIE chart. A new white point definition. No, it's not a new white point definition. It's D65. It's exactly the same what we're used to. And the Luma transfer function. The formula that's used to derive the monochrome Luma signal from the RGB. And this brings us to something which I was kind of aware of for a long time. There's a guy called Charles Poynton. He's a very famous broadcast engineer in the States. Sort of thinker on colorimetry and things like that. And he's had this sort of bee in his bonnet for many years about constant luminance. So if you think about the way a television camera derives that YCBCR, luminance and two colour difference signals currently, it does it from the RGB signals that come out of the three colour pickup sensors, the three CCDs, But having had the gamma of the system, that non-linear response applied to the RGBs before the luminance is derived, and Charles says, no, this is a terrible way to go about things. You should derive the gamma once you've derived the luminance signal, and
just it's worth backing up because the gamma was itself a kludge. It was there to get over, if I've understood it correctly, was to get over the nonlinearity of the original CRTs. Is that right?
Absolutely. So CRTs don't have a constant kind of signal in, light out relationship. We use a gamma of 2.2, which is that sort of classic kind of curve that isn't the straight line of signal in, light out. We've got this classic kind of gamma curve of 2.2 if you plot it on a graph. That says.
So that meant when you put, let's say, a low voltage in to represent a dark grey, you didn't get twice as much. When you doubled that voltage, you got a...
Exactly. And in fact, it works in the favour of a television system because the gamma concentrates a lot more of the dynamic range of the signal down in the low end. It means you get a lot more colour differentiation, a lot more luminance differentiation down in the low end, and consequently a bit better noise performance in the low end, which traditionally is where the tubes of old school television cameras suffered.
Yeah.
So it seems like almost a philosophical thing, for Poynton about constant luminance. I don't really understand where the differences are. He claims that there are tiny colour errors that are introduced by applying the gamma at the RGB stage rather than applying it at the luminance stage. And I haven't done enough research to know whether we still even need gamma in television, whether LCDs and OLEDs and plasmas and projectors even require it anymore. I'm sure the manufacturer applies a matrix at the last point before they display the colour on their display device, be it an LCD or an OLED or whatever. But I don't know whether gamma is even necessary anymore.
Yes, it does strike me as if it's something which is it's a bit of a largish hammer. We've got so many possibilities for shaping the signal in any way we want as we deliver it to whatever device. even during the course of delivery. Why do you need this one constant that doesn't change?
Yeah, so like you say, we've got a few tiny little hammers at the right places that are sorting this out. Why do we still need gamma hammer? Anyway,
But we do, and it is there.
Something to ponder. The other thing that came out is that obviously all the people you can buy equipment from at the moment for 4K have sat very firmly on the 30 frames per second progressive frames per second, and in fact ultra high definition television doesn't even allow for interlaced, which is nice that we're moving away from that. But so if you think about ultra high definition television at 4K, that's 4 times the resolution of regular HD. So if regular HD is 1.5 gigabits per second going down the cable, then you'd think if you could multiplex those all together, it would be a 6 gigabit per second signal for 4 times the resolution, if all you wanted was 30 frames a second most. And in fact, that's what Blackmagic are hawking. That's all their products that support 4K are. They're calling it 6G. 6G isn't yet a ratified standard by the EBU or the SMPTE, so they've kind of they're kind of flying solo, really. It works between Blackmagic products, but who knows how much further it'll go. But so 6G kind of covers the very basic end of 4K. But one of the really interesting presentations was a chap called Richard Salmon, who's a BBC engineer, and the experiments they've been doing between the BBC and the NHK, they've discovered that because you have kind of so much more resolution at 4K. Imagine a camera panning across a crowd in a sports stadium. As the camera's panning, if you've only got 30 frames per second of temporal resolution, then by definition, every single pixel is going to be a bit smeared. Every single bit of detail in the picture is going to be a bit smeared because the camera was moving for quite a lot, for a long time, a 30th of a second. But when the camera lands on a still shot, all of a sudden your brain is aware of how much resolution is there. The fact that you can see great detail in people's faces, you can see lots and lots of resolution which you're not used to on a
edge
on a
detail
display.
Suddenly comes flying out.
And they've discovered that at 4K and 8K people actually feel nauseous when they get this effect of the panning camera looks much like an old standard definition television picture. As it settles, you're aware of loads and loads of resolution. It's the difference between what they call static resolution and dynamic resolution. I've got one of Richard's slides up at the moment that shows the difference in standard definition terms, which is not offensive. And apparently, at the higher you go up, in higher definition terms, the more offensive it becomes. And he's got some still frame grabs of video shot at 50 frames per second and 300 frames per second. And they played us some on the big projector in BAFTA there, and it really did look splendid. The stuff that was shot at, greater than 100 frames a second looked brilliant. And so the proposal is that for ultra high definition television, we really do need 120 frames per second at least for it to look nice for live production.
So we're talking about the HD standard at the moment stops at 30. 30 frames a second, is that right?
Yeah, well, so the 1080p, maximum of 60 progressive frames per second is what we have at the moment. So we can have 60 frames per second at HD, and that goes down a 3G cable, which we're kind of all used to. It's an HDCam SR recording on a 5800 video recorder, if you will.
And so then the Blackmagic 4K 6G, is that right? Is capped at, is that 30 frames a second?
That tops out at 30 progressive frames a second for 4K, yeah.
But that gets you this slightly nauseous, or possibly even very nauseous effect. That you can now see the difference between the temporal and static resolutions.
Yes.
So the smear suddenly goes sharp, goes smeary, goes sharp, and that's going to be upsetting. So where does that fit in with the visual difference in 48 FPS that The Hobbit was shot in?
Well, okay, so The Hobbit was shot, I believe, on Red Epic cameras. So this is entirely kind of film file based. So there's no suggestion that there's any kind of HD SDI to move this stuff around. It comes off the camera on a portable recorder. As a bunch of DPX files. No, as a bunch of red code files. So in a sense, that's a lot of what they talked about at BAFTA was concerning live production. So sports stadiums, things like that.
So put that to one side.
So we really have to think about how do we move these things around on cables. So there we go. If we're saying we want 4K not at 30 frames per second, which we can just about send down a BNC cable and we'll call it 6G. But we want to do it at 120 frames a second, 4 times the frame rate. We're now looking at 24G, 24 gigabits per second down a piece of coaxial cable. It probably won't be a bit of coaxial cable. It'll probably be a bit of fibre cable, a bit of single mode fibre. But I've just popped up on screen some research I did sort of three years ago concerning 3G down coaxial cable. And it's just a load of iPatterns, basically, that show you what damage is done to a 3G signal as the cable length increases. And we kind of concluded, and we've applied the same standard for all our installations, that at 60 meters per second, at 60 meters, using the highest quality coaxial cable, you're just on the point of your signal starting to have too many errors that aren't recoverable.
Yeah.
So, as every superhero knows, you double the data rate, you kind of have to really half the cable length. So at 24G, we're looking at, at best 10, 15 meters of cable. At best, that's unusable, really, for a coaxial standard. So it does seem that, for any contemporary 4K television system that will be adopted, we won't be looking at coaxial cable. We'll be looking at fibre optic cable.
Okay.
And that's still in the YCBCR colour space. If we want to go for RGB, it's going to be even bigger, 36G for 4K and 120 something G for 8K. It's just untenable, really. But what that also brings to us is this idea that maybe we won't be just sending things around as pixels. We'll have to have some sort of mezzanine format, and we'll talk about that in just a little short while, because I wanted to kind of wrap up the whole sort of discussion of cable standards with just a reference to HDMI, because obviously HDMI is the domestic standard. That's how you get things out of your Blu-ray player into your telly, or from your set-top box into your telly. And so HDMI 1.4, which is the current standard that's with us, that tops out at about 8 gigabits per second, and so it does support 4K at 30 frames a second. So it supports like a very sort of slimmed down version of 4K. But HDMI 2 apparently extends much further and really mimics some of the developments in DisplayPort technology. So that will take us all the way up to high 20s. So it's the thinking is that HDMI 2 will support 4K at those greater than 100 frames per second frame rates. So it's
but quite short cable runs. I mean, these are sort of 2 or 3 meters max.
Yeah, set-top box to telly, topping out typically at no more than 10 meters, that kind of thing.
Yeah.
So, I mean, with all that kind of monstrous data load in mind, the next presentation that really caught my eye was by this chap called Professor Philip Willis, who's a computer graphics guy at Bath University. Just got his personal page up from Bath University, and he was a very engaging speaker, and he talked a lot about pixel-free and even frame-free video. And you think, hang on, how can
this is pretty exciting.
This is how can you capture video without chopping up into pixels and lines and frames and such? But he showed a system that they've been developing for a few years now, and I'm just going to play a YouTube clip. And so what we're seeing here is his codec takes. In fact, I'll pause it to sort of slightly explain it a bit better. His codec takes the pixels of a video clip, and it doesn't matter what resolution, and it transforms them into a series of contours and vectors. So contours are continuous mathematical descriptions of surface edges and how they're shaded, and then the vectors describe how they're moving. So there's kind of elements of how MPEG works, how the macro blocks move in MPEG, but he has essentially done away with any reference to resolution within each frame of video. He's just got continuous contours. The upshot of this is that you basically render the image at the resolution you choose, and because these were all vectors and contours describing the image and the shading of the various parts of the image.
And that's an important part, the shading, because that's the vectors are just lines or points being connected, but
yes.
The shading is what goes in between.
Yeah, exactly.
That's what was puzzling me. I see. Yes,
that's what makes pictures as opposed to line drawings. Yeah.
Yeah.
Now, I've paused it on a frame showing a clip from a soft drink commercial, and the screen has been chopped in half, and on the right hand side of the screen, they've just rendered the contours and vectors as if they were video, so you can kind of see what it looks like inside the codec. It's quite an interesting sort of image.
Yeah.
And apparently, so far they've made no efforts to make this a compression system. There's no suggestion that this will reduce the data load of video, but it is a way of divorcing video from pixels. And so you could imagine that this technology would be incorporated into the camera, and we'd just be distributing this data stream around the place that describes the pictures. So we could then render them, and presumably you can do with the right processing, you could do grading, you could do effects, you could do lots of stuff
in this amazing manipulations.
Yeah, vector contour domain. You don't have to render it back to pixels to do those things, and you'd only render it back to pixels when it landed at a display device. That's kind of, I think that's kind of a really kind of fundamental change in the way that telly will work, and the tantalising little thing that the professor said at the end of his talk was, and we're also investigating making contours and vectors non-time dependent, so that they work across time as well as per frame of video, so we could divorce video from even having frames. So you could shoot something which is entirely resolution less and frame rate less, and then you render it at the correct resolution and the correct frame rate for the display device that you're watching it on. And so all of a sudden, standards conversion disappears, and up-resing, down-resing disappears. Everything's kind of gone. It's all just as good as it can be. And the other upshot of this is that because everything's described in curves and vectors and shading, of course you can't get more detail than was shot by the camera on the day, but when you do up-res things, they don't alias in the way that up-resed video does, where you get jaggies and stuff like that. Yes. Edges remain smooth, and so it produces up-resed images that are pleasing compared to up-resed images of standard definition to high definition, where at best it's always a bit of a bodge, and that shot looks very soft.
When you zoom into when you zoom into something in a pixelated image, the best that can do is produce steppy, jaggy corners. Whereas if you know that it's a curve from here to here and you zoom into it, well, it's still a curve from here to here. If in real life, when you did zoom into it, there was more detail, well, you won't get that because you didn't shoot it. But at least you'll get a pleasing curve. So it would be much more accessible to the human eye. Yes, much better.
For sure. I'm just popping up the prof's paper that talks about all this, and it's surprisingly accessible, actually.
Yes, because you did your degree in maths, didn't you?
Maths and programming, and I did my final year in graphics. Yeah.
And was it, having looked at the maths, it didn't look like it was all that heavyweight.
If you're comfortable with vector maths, then it's just fine. And actually, I mean, I've given a very poor description about it because the contours actually have hierarchies. So if you know anything about computer graphics, that's not a hard concept to get into. Lots of particularly volume mapping systems use hierarchies for that kind of stuff. So none of this is kind of harder than A-level maths, I would say. It's remarkably accessible. He's done a very good job of explaining it, and he was a fantastic presenter. If you get the chance to see this, I'd encourage you to. You can grab all the presentations from the Beyond HD Masters website. So it's well worth looking at. And so I thought it was a splendid day. There were some real points of sort of technological so that's how they'll do it. There was an awful lot of the manufacturers just being sort of sore about the fact that tellies aren't selling as well. The thing I heard from several manufacturers, which I just couldn't believe, was, of course, 4K will be the saviour of 3D. And I just kept thinking to myself, surely, the loss of vertical resolution wasn't the problem with 3D. It was the fact that you've got to put glasses on, which breaks the paradigm of casual television watching. That's what killed 3D,
Yeah, absolutely. I don't think we're there with 3D. I think it was something of a hoodwink, which hasn't worked really. So,
well, I mean, the more cynical people say, kind of it comes around every sort of 30 years. You know,
Yeah.
it was anaglyph back in the 60s, and you know, it kind of came round again. And but there was a company showing a modified LG panel that was glasses free 3D, uses a lenticular you know, Fresnel lens incorporated into the display,
Yeah.
and if you got your head just in the right place, the 3D effect was kind of okay. It wasn't as compelling, say, as Dolby Cinema 3D is, but as soon as you kind of relaxed your head and you moved off axis a tiny bit, you were aware of chromatic distortions around the edges of things and stuff. So, you know, I think even Glasses 3 3D, and until you can get what R2D2 does in Star Wars,
Yes.
and project a little picture of Princess Leia in free space in front of him, I don't think 3D's ever going to hit.
Well, there we are. So it was a very worthwhile day, fascinating, and I just love this idea of losing the frame rates and losing the pixel resolutions and just moving to the new mathematical way of simply describing the curvature and
it just seems more honest,
shading.
Doesn't it?
Fantastic. Yes, it does.
And in one sense, I suppose it's the reverse of what things like PostScript do. You know, like you look at a PDF and it's taken a vector description of a page and turned it back into a raster for you. This is the reverse of that. It takes the raster, turns it back into a vector description of the image. Very interesting.
So SVG, here we come. Is that the idea?
Yeah, I think so. Yeah. Scalable vector video.
Yes, SVB.
Yeah.
Well, thank you, Phil. Fascinating for a short one. I don't know what the next podcast's topic is. Have we thought of a couple?
The two things I've kind of got bubbling. One is Homebrew Hardware Part 2, Raspberry Pi and Netium network control boards, or this thing I've been banging on about a lot for the last year, the Amulet KVM over IP system, which obviously you've been sort of looking at professionally for a job you're working on. So maybe we could talk a bit about that.
We should get young James to talk about it.
Yep, get the Hunter in. That'd be good. Yeah. Yes,
James is the engineer I've been working with on a project, which is what we've just been mentioning. Right, excellent. Well, thank you, Phil.
Jolly good.
Let's speak to you soon, I suppose.
Back to Call of Duty with your young man.
Back to Call of Duty, yes. Dad, he said, you're absolutely hopeless.
Oh, well. I'll see you soon, chap.
And you, bye.
Take it easy.